Hi, I'm Dr. Incognito. In this video, we're going to compute limits numerically. So we're computing limits numerically. As an example, we're going to look at the limit as x approaches 0 of sine x divided by x. So before we try to compute limits using any special technique, let's simply plug in 0 for x. We would get the sine of 0 divided by 0, and the sine of 0 is 0, and so we get 0 over 0, which is an indeterminate form. So our method for actually, I'll say guessing this limit is to plug in values of x near 0 and then use my calculator to compute the fraction sine of x divided by x. So I'm going to make a table of values. I'm going to pick values of x, and then I'm going to compute values of sine x over x. So for x, the values that I want to pick are supposed to represent what's happening here. What is x doing? X is approaching 0. So I should pick values of x that are close to 0. So for starters, I'll pick something like 0.5. And then I'll use my calculator to compute the sine of 0.5 divided by 0.5. Let's do that. Sine 0.5, which is about 0.479, divided by 0.5, and I get 0.9589. 0.9589, rounding off to 4 decimal places. And I'm going to continue this. I'm going to pick more values of x and continue to calculate sine x over x. And I'm going to see if I notice any kind of a pattern. So let's try something, again, x is approaching 0, so I used x equals 0.5 here. I want to now get closer to 0, so I'll pick, how about 0.1? So the sine of 0.1 divided by 0.1. Sine of 0.1 divided by 0.1. And I get 0.9983 to 4 decimal places. And let's try another one. Let's make x even closer to 0. X is approaching 0. It can get closer than 0.1. How about 0.01? So sine of 0.01 divided by 0.01, and I get 0.99998. I needed a 5th decimal place there, or else I would have just rounded up to 1. So that's very, very close to 1. And let's just try one more. Let x get closer. 0.001 for x. So I'm going to try the sine of 0.001 divided by 0.001. And I'm getting how many nines is that? 2, 4, 6 nines and an 8. 9999998. So it appears numerically that as x gets closer to 0, the function sine of x divided by x is getting closer and closer to 1. So I will guess that the limit as x approaches 0 of sine x over x is equal to 1. Technically, that is just a guess. More sophisticated methods are necessary to actually verify that that is indeed correct. A couple of comments. One is that when we're doing calculus involving the sine function here, our calculator should be in radian mode. So this was 0.5 radians, 0.1 radians. If your calculator is in degree mode, then you would get different values here. And more importantly, this limit is a two-sided limit. It says here that x is approaching 0. There's 0. One possibility is that x is over here and approaching 0, and that's what I did here, 0.5, 0.1, 0.01, etc. But another possibility that's equally valid is that x is on the left side of 0, in which case x would be negative, and approaching 0 from the left side. So technically, the information that's here is only allowing us to guess that the right-hand limit is 1. So we should take a moment and investigate the left-hand limit by plugging in values of x near 0, but on the left of 0. So x sine x over x, instead of picking 0.5, which is on the right of 0, let's pick negative 0.5, which is on the left of 0, and try the sine of negative 0.5 divided by negative 0.5. And I'm getting 0.9589. Oh, that's the exact same value that we had there. Maybe that's a coincidence. That should have been negative 0.5 there. Negative 0.1. So let's try the sine of negative 0.1 divided by negative 0.1, and I get 0.9983. That's again the same. It looks like I'm getting the same exact values when I plug in a negative value as the corresponding positive value, so that makes me scratch my head and wonder if that's always the case. And indeed it is, because of this property. The sine of negative theta is equal to the negative of the sine of theta. This is an interesting symmetry property. If this is the unit circle and this is an angle theta, then the sine of theta would be the y-coordinate of that point, and the angle negative theta will give you the exact opposite y-coordinate, so that the sine of negative theta would equal the negative of the sine of theta. And this is saying that the sine of theta is an odd function. An odd function in general has the property that f of negative x is equal to negative f of x. So the sine function is an odd function. And now if we look at our fraction with negatives plugged in, take sine x over x, but plug in the negative. Sine of negative x over negative x is equal to, according to the oddness of the sine function, this is negative sine x over negative x, and now you just cancel the negatives and you get sine x over x. So you can see that you're going to get the same output whether you put in a number or it's negative. So it's no coincidence that these values are exactly the same as these. So the next two will also be exactly the same, and we will be able to conclude that the limit as x goes to 0 from the left of sine x over x is also 1. And since the limit from the left is 1 and the limit from the right is 1, we can drop the superscript plus or minus, and we can simply say that the limit as x approaches 0, independent of direction, is equal to 1. So this is how we compute the limit numerically. Technically, it's just a guess. We're using numerical observations to guess at the limit. And this particular limit has some significance. If I draw the curve y equals sine x, this is the curve y equals sine x. It turns out that this limit, which is 1, is the slope of the tangent line to the curve at this point. So if I draw the tangent line in here, the slope of this tangent line is 1.